Throughout this video, we will looking at the fundamental forces that drive the weather system so that you can understand and predict what the weather will do at any time or place, given the basic data. The weather, the wind and rain, cloud and fog, heat and cold is the visible result of movement of energy through the lower atmosphere. Although forecasting small-scale weather is very difficult, it is relatively easy to follow the rules that determine weather in the large scale, and to explain, for instance, why it is hot and dry in the Sahara or rainy in the Amazon basin. We shall see in the chapters that follow how these rules are developed, and it will all come together in the sections on climatology. We start at the beginning and look at the composition and structure of the atmosphere. The composition of the atmosphere. The atmosphere is a mixture of gases, including water vapor, some solid particles like dust and smoke, and some water in its solid or liquid form, which we see as clouds, mist, or fog. If we leave out solids, water and water vapor, and look only at dry air, we find that the relative concentrations of the gases are constant in the lower layer of the atmosphere, the troposphere, and we can lay down a basic mixture. It is nitrogen 78%, oxygen O2 21%, and carbon dioxide CO2, ozone, O3 and other gases 1%. Therefore, nitrogen is the largest constituent of the atmosphere. Remember, these are percentages by volume in dry air. Surprisingly, most of the gases are inert as far as the weather is concerned, carrying only limited amounts of energy as hot and cold air. The three that play an important part in the weather are the very small percentages of carbon dioxide, ozone, and water vapor. Water vapor, which carries large amounts of latent heat energy, is a light transparent gas. It averages less than 1% by volume, but its local concentration varies from 0 to 4%. Most of the water vapor in the atmosphere is found at low altitudes and in areas of higher air temperature, the tropics. The sun's energy reaches the earth as short-wave radiation, and little is absorbed or reflected by the atmosphere before it warms the earth's surface. Long-wave radiation is then emitted back into the atmosphere from below, some of which is absorbed by the carbon dioxide and water vapor, causing the so-called greenhouse effect. Ozone, an allotrope of oxygen, made of 3 oxygen atoms rather than the usual 2, is most concentrated in a layer in the upper stratosphere between 50,000 and 100,000 feet, which is around 15 to 30 kilometers. Ozone absorbs harmful ultraviolet radiation from the sun. As the ultraviolet radiation is absorbed, it causes a temperature rise in the upper atmosphere. The maximum heating occurs at the top of the ozone layer, around 160,000 feet, or 50 kilometers. Pressure, temperature and density. In the atmosphere, there is a fixed relationship between temperature, pressure and volume. The general gas law is pressure multiplied volume equals gas constant R multiplied temperature, where R is a gas constant for the gas or mix of gases we are dealing with. In Meteo, we are most concerned with the density of the atmosphere, so we need to do some shuffling of the equation. Density is defined as the mass of a unit volume of gas, so for a fixed mass of air, density is inversely proportional to volume, meaning that as the volume goes up, the density goes down. we can rewrite the equation. So density is directly proportional to pressure and inversely proportional to temperature. This means that at constant temperature, the pressure goes down, the density goes down, while at constant pressure, if the temperature of the air is higher, it is less dense. Note: air density is directly proportional to pressure and inversely proportional to temperature. This relationship is crucial to the development of vertical movement called convection in the atmosphere. For air warmer and therefore less dense than its surroundings will rise and continue rising, while air that is colder than its surroundings will sink. Note: warm air rises, cold air sinks. Pressure. Pressure, which is a force per unit area, is measured in bars, but specialists use the more convenient millibar, 1/1000th of a bar, abbreviated to MB. ICAO use the hectopascal, 100 pascals, which is happily exact the same size as the millibar. The average pressure of the atmosphere at sea level over the whole world is 1013.25 millibars or hectopascals. Pressure is measured by a barometer, and the most common type is the mercury barometer. If you fill a closed column with mercury and invert it in a dish, the mercury will stabilize at about 30 inches high. Atmospheric pressure is pushing on the bottom of the column, but to stop is closed, and the only pressure there will be the very small pressure from mercury vapor, effectively zero. The column is therefore held up by atmospheric pressure, and by measuring the height of the column, you can determine what the pressure is. With a suitable scale, you can read this height of a pressure in millibars or in any other unit. You will recognize here the origin of the American way of giving barometric pressures in inches of mercury. A second type of barometer is the aneroid barometer. This uses a closed evacuated aneroid capsule that expands and contracts under changing pressure. An altimeter ultimately is an aneroid barometer. You can occasionally also come across references to barographs. A barograph is an aneroid barometer that records changing pressure in graphical form. Temperature. Temperature in meteorology is given in degrees Celsius or centigrade, where 0 is the freezing point of water and 100 degrees the boiling point of water at sea level pressure. For calculations in the thermodynamics, two equations only work out if you use the scale of absolute temperature, or Kelvin, in SI units. On this scale, although the degrees are the same size, absolute zero is minus 273 degrees, thus 0. In the same as minus 273 degrees and 100 degrees is 373 Kelvin. You may also come across the Fahrenheit temperature scale, on which the freezing point of water is at 32 degrees Fahrenheit and the boiling point of water is at 212 degrees Fahrenheit. This temperature scale is now falling into disuse and is generally regarded as obsolescent. Density. Density in meteor is measured in grams per cubic meter. On average, as we said, the pressure at sea level is 1013.25 millibars. The average temperature at sea level is 15 degrees or 288 Kelvin. Using the correct gas constant for dry air, we get an average density of 1225 grams per cubic meter. Note that if water vapor is present in the mixture, we will get a lower density for the same conditions of temperature and pressure. Water vapor has a sea level density of about 760 grams per cubic meter, rather over half the density of the dry atmosphere. Most air is less dense than dry air at the same temperature and pressure. The vertical structure of the atmosphere. The molecules of the atmosphere are attracted by the Earth's gravity at any height above the Earth. The pressure is proportional to the mass of air above. Thus, the pressure in the atmosphere is higher at low altitudes. Therefore, the density is higher too. The rate of change of pressure with height is not linear. Figure 1.4 shows how pressure reduces with height in the atmosphere. Upper air data is usually collected by a radiosonde, a balloon with an instrument pack that records temperature, pressure and humidity information and radios it back to the ground station. Radar tracking of the balloon can give upper wind data as well. It is important to remember that pressure and density always reduce with height. Differences in temperature in the atmosphere only affect the rate at which pressure and density fall. Pressure and density fall more rapidly in cold air than in warm air as height increases. This point is so fundamental to the understanding of the behavior of the weather system that it is worth repeating with another diagram. Figure 1.5 shows the pressure at height in two columns of air, one warm and one cold, where the sea level pressure is the same. At any chosen height, the pressure aloft in the warm air column is higher, and if you choose any pressure level, 700 hectopascal in the diagram, it will be at a greater height above sea level in the warm air. Note, a warm air mass means high pressure aloft, and a cool air mass generally means low pressure aloft. You will need to be aware of some of the basic data recording height to pressure in a standard atmosphere. The important numbers are the heights in feet of the 700 hectopascal, 500 hectopascal and 300 hectopascal levels, and also the number of feet per millibar at sea level. If you are asked to solve problems relating to height and pressure at reasonably low level, for terrain clearance for example, and no figure is given to you, use 1 hectopascal equal to 27 feet as a good approximation. The large-scale atmosphere. Up to this point, we have looked at the composition of the atmosphere from the surface out to about 15 kilometers. We still need some general knowledge of the bigger picture out to 100 kilometers. This figure shows the large-scale atmosphere out to the edge of space. The lowest layer is called the troposphere, meaning the sphere of turning or mixing, and this is where most of the weather occurs. Half of the atmosphere by weight lies in the lowest 5.5 kilometers, 18,000 feet, of the troposphere. The remaining 5.5 kilometers contains another 25%. The troposphere also contains 90% of the water vapor in the atmosphere. Note, 50% of the mass of the atmosphere lies in the bottom 5.5 kilometers of the troposphere. We shall see later that the troposphere is heated by the Earth beneath it. For this reason, the temperature in the troposphere generally falls with height until it reaches the tropopause, the boundary between the troposphere and the stratosphere. Above the tropopause, which on average is at about 11 kilometers, is the stratosphere. In the upper two-thirds of stratosphere is the ozone layer. The temperature in the stratosphere stays constant just above the tropopause, then steadily increases, rising to a maximum at the stratopause, then reducing again as the atmosphere thins still further. The stratopause, at about 50 kilometers or 164,000 feet, marks the boundary between the stratosphere and the mesosphere. Above the mesosphere lies the thermosphere, also known as the ionosphere, and the exosphere. The atmosphere in the exosphere is so rarefied that we would consider it to be space. The space shuttle orbit is in the exosphere, whereas commercial aircraft operate in the lower stratosphere or upper troposphere. Variation of tropopause height with latitude. The tropopause effectively marks the limit of vertical movement in the air, and therefore the upper limit of significant weather. Although the average height is 11 kilometers, it is higher and colder than this at the equator and lower and warmer at the poles. Note, the tropopause height is greater and the tropopause is colder at the equator. The breaks in the tropopause shown in this figure reflect the positions of the polar and subtropical fronts, which we shall meet later. Variations of tropopause height with season. The tropopause is usually higher where the mean troposphere temperature is higher and lower in lower temperatures. At the poles and at the tropics, the troposphere temperature remains roughly constant throughout the year, but at mid-latitudes winter and summer temperatures differ significantly. Note, the tropopause heights vary in the mid-latitudes, higher in summer, lower in winter. Typical tropopause heights for latitudes 30 degrees, 50 degrees, and 70 degrees in summer and winter are the standard atmosphere. ICAO has defined a standard atmosphere for instrument calibration purposes and as a benchmark for comparison. The average values for sea level pressure, temperature, and density were taken as the starting point and the average change of temperature with height added on. You have already seen the average sea level pressure, temperature, and density figures. 1013.25 hectopascal plus 15 degrees and 1225 grams per cubic meter. The average change of temperature with height, the lapse rate, is 1.98 degrees Celsius per 1000 feet, 6.5 degrees Celsius per 1000 meter, up to a tropopause at 36,090 feet or 11 kilometers at minus 56.5 degrees Celsius, when temperature remains constant to 65,617 feet or 20 kilometers before rising slowly again at 0.3 degrees per 1000 feet or 1 degree per 1000 meter. To correct from ESA to the real world, you have to work out the ESA deviation, the difference between the calculated ESA value for temperature at the specific height and the real environmental temperature, the outside air temperature, OAT. The OAT will be given to you and calculated to ESA temperature by using a lapse rate of 2 degrees per 1000 feet from a surface temperature of 15 degrees Celsius. This will be close enough to get the right answer. Thus your ESA temperature is ESA equals 15 minus height in thousands of feet multiplied 2, or ESA equals 15 minus height in kilometers multiplied 6.5. To find the deviation, check the difference between ISA and OAT. OAT is the higher temperature. The ISA deviation is positive. If it is lower, the ISA deviation is negative. Altimetry. Pressure settings and Q codes. Altimeters have a barometric setting control which can be adjusted so that the altimeter reads heights above different datums. The four main datum settings are QFE. QFE is a reading of station pressure taken on an accurate barometer and adjusted for any difference in height between the barometer and the field elevation. If QFE is set, altimeters should read 0 on the ground at the airfield. QNH. QNH is the station pressure, QFE, adjusted down to mean sea level, MSL, using ISA values for the temperature between the station and MSL. Since the altimeter itself uses ISA values for its internal calculations, an altimeter with QNH set should read station elevation on the ground at the station. Standard pressure. Standard pressure 1013.2 hectopascal above a set altitude called the transition altitude aircraft operate with a standard pressure setting of 1013.2 hectopascal. The heights indicated are called pressure altitudes. They may also be given in an abbreviated form by knocking off the last two zeros. This is called a flight level, FL. Thus, a pressure altitude of 30,000 feet equates to flight level 300. QFF. QFF is the station pressure adjusted down to mean sea level, using the actual station temperature in the calculation. This is not set on aircraft altimeters, but used by Meteo service as an accurate value for mean sea level pressure. QFF is the pressure displayed on surface isobar charts. QFE and QNH are available in various forms. Airfield QNH applies at the airfield. In UK airspace, away from airfield and below the transition altitude, a regional QNH is used. This is the lowest forecast QNH for the region for 1 hour ahead. Using the lowest of all the forecast QNH values gives the maximum safety margin. Airfield QFE is the pressure at the highest point of the airfield surface, again given the greatest safety margin. And if the touchdown point of the instrument runway in use is significantly below the high point, then a touchdown QFE will also be given. Finally, QNE. QNE, this is not a pressure setting at all, but is the touchdown height that will be indicated on the altimeter if the standard setting 1013 hectopascal is set. In other words, it is the pressure altitude of the touchdown point. This procedure is used at high airfields like La Paz in Bolivia, where QFE would be too low a value to set on an altimeter subscale, and also when the QNH is too low to set on the subscale. Changing the subscale setting. When the pilot changes the altimeter subscale setting, the reading on the altimeter changes because the altitude is being referenced to a different datum. Example, for takeoff, the altimeter is set to the QNH 1003 hectopascal. The transition altitude is 3000 feet on the QNH. As the aircraft passes through the transition altitude, the pilot resets the altimeter subscale to 1013.2 hectopascal. What will the altimeter read at that point? Solution. Draw a sketch diagram marking in the two pressure datums. Notice that the higher pressure is lower down. The difference in pressure of the two datums is 10 hectopascal, which, using 27 feet per hectopascal, is 270 feet. The diagram shows that 3000 feet on a setting of 1003 hectopascal equates to 3270 feet on the standard setting. For Altimetry problems, we normally use 27 feet or 8 meter per hectopascal. Barometric errors. If everything is correctly set, using the QFE will indicate height above an airfield. QNH will indicate altitude above mean sea level, and using the standard setting will indicate the pressure altitude or flight level. Surface pressures change, though, and if an incorrect pressure setting is left on the altimeter, it will indicate higher than it should, overread, or lower than it should, underread. This is called barometric error. Barometric errors are particularly dangerous if you fly from high pressure to low, for then the altimeter will overread. An aircraft has the correct QNH set at point A and the altimeter indicates altitude above mean sea level. Without resetting the subscale, the pilot flies to point B, an area of low pressure. Because the QNH datum he has chosen is below sea level, his true altitude is now less than his indicated altitude, and his obstacle clearance is compromised. High to low, careful go. Example: an aircraft is parked overnight with the QFE of 1008 millibars set on the altimeter subscale. The following morning the correct QFE is given as 1002 millibars before the subscale is reset, and assuming 27 millibars per feet, what will the altimeter read? Solution: the pressure difference is 6 millibars at 27 feet per millibar. The height difference will be 6 multiplied 27 equals 162 feet. Use the law high to low, careful go, means the altimeter will overread. An aircraft departs point Q at an altitude of 1500 meters with the QNH set at 1010 millibars. It arrives over point R where the QNH is 990 millibars and there is an obstacle 1000 meter high. Assuming 8 meters per millibar, what will be the obstacle clearance over R? Once again, the altimeter will be overreading. The size of the barometric error will be 1010 minus 990 equals 20 millibars. At mean sea level, this is equivalent to 20 multiplied 8 equals 160 meters. The aircraft above mean sea level altitude will be 1500 minus 160 equals 1340 meters. And the obstacle clearance will be 340 meters. In a similar way, aircraft true altitude can be found at any given flight level if the QNH is known. QNH is the pressure at mean sea level, so the difference between true altitude and flight level is the height difference between QNH and 1013 millibars. If no value is given, assume 27 feet per millibar. Example: an aircraft is at flight level 40. What is the above mean sea level altitude if QNH is 998 millibars? QNH is at lower value than 1013, so the aircraft above mean sea level altitude will be less than its pressure altitude. The size of the difference will be 1013 minus 998 equals 15 millibars. This is equivalent to an altitude error of 15 multiplied 27 equals 405 feet. The aircraft above mean sea level altitude is therefore 4000 minus 405 equals 3595 feet. Temperature error. Even if the barometric settings on the altimeter are correct, true altitude will differ from indicated altitude if the temperature differs from the ISA values. It was explained earlier that in high temperature air masses, any given pressure level will be at greater altitude than in cold air masses. Altimeters measure pressure, so will show the same altitude at the same pressure level irrespective of any temperature difference. This figure illustrates the problem. In ISA temperature conditions, the 700 millibar level is almost exactly 10,000 feet. In colder air, the 700 millibar level, which the altimeter thinks is 10,000 feet, is in reality much lower. In low temperatures, therefore, the altimeter overreads, and in high temperatures, it underreads. Air mass temperature deviation from ISA makes no relative difference to height keeping for air traffic reasons, for all aircraft will have the same error. However, as you can see from this figure, the absolute separation between pressure levels is reduced in cold air. This means that while there is a theoretical height separation between flight level 300 and flight level 310 of 1000 feet in ISA conditions, the separation will be less in cold air, and in warm air it will be greater. It is possible to calculate exactly the altitude correction for the given air mass temperature. This is best done on a flight computer and is covered fully in the instruments section of these videos. There is, however, a rule of thumb approximation that can be quickly applied. The ground rules are: barometric error can be calculated separately and it should be dealt with first. The temperature correction applies to the band of atmosphere between the level where the altimeter reads correctly and the aircraft. This datum level is station elevation for airfield QNH and touchdown for QFE. If sea level pressure QFF is given, the datum is sea level. ISA deviation can be assumed to be the same at all heights. Pressures are whole millibars rounded down. That done, the calculation is that there will be a 4% height difference in true altitude from indicated altitude for every 10 degrees difference in air mass temperature. That is for every 10 degrees of ISA temperature deviation. Note, 4% of height difference for every 10 degrees of temperature difference. Example: if you are flying at flight level 200, outside air temperature is minus 40 degrees Celsius and the pressure at sea level is 1033 hectopascal. What is the true altitude? Solution: barometric error first. The 1013 datum is 20 multiplied 27 equals 550 feet above mean sea level. The ISA deviation is minus 15 degrees. The correction for temperature error is 1.5 multiplied 4% multiplied 20,540 equals 1232 feet. The air is colder than ISA, so the altimeter is overreading, and the true altitude is 20,540 minus 1232 equals 19,308 feet. Notice that the temperature correction has been applied over the full height as we were given a QFF. The relation between QNH and QFF. QNH is calculated from station pressure on the assumption that ISA conditions apply. QFF is the actual sea level pressure. This means that when the temperature is different to ESA, QNH and QFF will differ. This figure illustrates the situation for an airfield above sea level. In this case, if the column of air is colder than ESA, QNH will be less than QFF, higher, and if the air is warmer than ESA, QNH will be more than QFF. For an aerodrome below mean sea level, the reverse applies. In air colder than ESA, QNH will be greater than QFF. In warmer air, QNH will be less than QFF. So why does setting QNH on the ground give you the correct airfield altitude above mean sea level? The answer is that the altimeter is calibrated to ESA. If you set QFF, you would have to apply a temperature error correction even to get the correct reading on the ground. There is a follow-on from this. If the temperature differs from ESA, the QNH will only read the correct altitude on the ground. If you are airborne, you may need to apply a temperature correction to get to true altitude. In warm conditions, this is not dangerous because the true altitude will be higher than the indicated altitude. However, in very cold air and close to the ground, the temperature error may be critical as the true altitude will be less than the indicated altitude. An easy way to remember this is that when the temperature is low, the aircraft will be lower than indicated. It is essential, therefore, to make an altimeter temperature error correction when calculating minimum descent heights and decision heights in very cold conditions. The amount to add on to the indicated height or altitude to get the true value is usually derived from correction tables. Example: an aircraft is making a precision approach to an aerodrome at 4,000 feet above mean sea level at an outside temperature of minus 30 degrees. The decision altitude dA is QNH based at 4,200 feet. The decision height is 200 feet above touchdown. Solution: setting the QNH will cause the altimeter to read correctly on the ground, but not 200 feet above it. Enter the table at 200 feet and minus 30 degrees to find the correction of plus 40 feet. The indicated altitude of decision height will be 4,200 plus 40 equals 4,240 feet. Drift and altimeter error. The circulation around an area of low pressure in the northern hemisphere is anti-clockwise, and around a high pressure system it is clockwise. This means that an aircraft traveling from high pressure to low would experience starboard or right drift. It is equally correct to reverse the logic and say that if you have right drift in the northern hemisphere, low pressure is ahead of you. Of course, an aircraft flying from an area of high pressure to low would be experiencing a barometric error that would cause its true height to decrease. This means that it is true to say that in the northern hemisphere, if you fly a constant indicated altitude and have starboard drift, your true altitude is decreasing. Airflow over high ground. Airflow over high ground can affect the atmospheric pressure. Just as the airflow over a wing leads to a drop in pressure, so does airflow over a hill. In this area of reduced pressure, the altimeter will indicate a higher altitude than it should. It will overread. Additional height margins should therefore be allowed when flying over high ground in strong wind conditions. Density altitude. Density altitude is the altitude in the International Standard Atmosphere at which the air density would be equal to the actual air density at the place of observation, or in other words, the height when measured in terms of the density of the air rather than the distance from the ground. Density altitude is the pressure altitude adjusted for non-standard temperature. To calculate density altitude from pressure altitude, we need to know the temperature deviation from ISA conditions. The difference between pressure altitude and density altitude is 120 feet per degree of temperature deviation. Example: an aircraft is at flight level 100 and the outside temperature is minus 35 degrees. What is the density altitude? Solution: ISA at flight level 100 is plus 15 degrees minus 2 multiplied 10 gives us a temperature minus 5 degrees. Outside temperature is minus 35 degrees. Temperature deviation is minus 30 degrees. Pressure altitude at flight level 100, 10,000 feet. Difference between pressure altitude and density altitude, 120 multiplied minus 30 gives minus 3,600 feet. That gives us a density altitude of 6,400 feet. This means that the density of the air at an indicated 10,000 feet or flight level 100 on this cold day is the same as the density of the air in a standard atmosphere at 6,400 feet. You may not have performance data for your aircraft for ISA minus 30 degrees conditions, but you should have performance data for ISA conditions. To find out how your aircraft will perform at flight level 100 on this cold day, look at the data for ISA conditions at your density altitude 6,400 feet.